Good morning, everyone. I know we're starting a bit early today because Mrs. Wood didn't have anything to say really, so we're still waiting on a couple people to get into Blackboard, and that's okay. But if you're with me and you want to give me a green check so I know you're ready to get going, that would be great, and then we'll get started here in a minute. Perfect. What I would like to do today is I would like to just finish the first lesson from Unit 5, and then it won't take that long. It's not terribly long. And then you guys can ask any further questions you might have from Unit 4, and that'll be kind of it for Unit 4. So I was hoping that you could finish the Unit 4 learning guide, have it handed in today. I know there was a couple of you who submitted the learning guide either yesterday or this morning. And I didn't send out that password yet to you guys, so I apologize for not doing that, but as soon as I'm done in the studio here, I'll go back to my office and I'll have a look at your learning guides so you can have that test done either today or tomorrow. I know there's a few of you that are be coming in today, and I just want to remind everybody's welcome to come in today from 1 to 3, just into our building down here on Doyle, McWilliams Center, and any help you need or whatnot, if you need a quiet place to work, you want to write your test here, we can do whatever you guys need. So, yeah, looks like a few more people have come in, and everyone seems to be with me that's in here already. So, just going to clear those out. I'm just going to jump right into this, and then we will go through anything you might have had in terms of questions from last day. All right, so as I mentioned before, Unit 5 is on graphing. There's some sort of calculation stuff on functions, and we talk about the difference between functions and relations. And it's generally a bit of an easier unit because you're looking at graphs and you're interpreting graphs. There's maybe a bit more vocab involved with this unit. So when we say something like what's the domain or the range or the x-intercept, you need to kind of know what these terms mean. So we're going to spend some time talking about a few of the terms and then just essentially looking at graphs. So yeah, some of you will probably find this stuff fairly straightforward, which is really good. The first thing here is constructing your understanding. So we're going to look at a few graphs, and we're going to try to figure out what is going on in the graphs. You can see anytime you're given a graph or a chart, you need to look at the axes of your graph, so the vertical and the horizontal. So we need to make sure we know what the graph is saying. So this is speed, and this is time. Now, it might be a little bit confusing because there's no numbers written on this graph, so how do we know what's going on? If there's no numbers there, what does it mean? Well, instead of thinking about really specific values in terms of speed and time, just think about in general. What can we kind of assume from the graph? So let's look at our chart here. Down at the very middle here, we call this the origin, and we don't have any values here, but we could put in something like 0 for time, and we could put in something like 0 for speed as well. And most graphs will have little increments like this, kind of like a number line, same thing going up this way. So although there's no specific numbers on the chart, we know that something down here is going to be smaller than something up here. So if the speed was down here, it's slow, and up here it's going to be fast. Hopefully that kind of makes sense. And then this is at the very beginning, this is the start time, and then over here we have the end time. So that's kind of what these graphs are going to look like. They're not going to have, usually they won't have numbers on them. They'll just have a plot, and you need to just kind of determine what's going on. So the question here is, Michael rides up and down a steep hill on his bike. Which graph best represents his ride? So we have person on a bicycle riding up a hill and then down a hill. So what do we know about somebody's speed? If you're riding up a hill, are you going to be going fast or slow? If you're riding down a hill, are you going to be going fast or slow? And yeah, we kind of need to figure out which graph best represents the idea of starting off. We have here's our little bicycle, and you're going up a hill and then down a hill. So the one most common sort of mistake students will make is thinking, okay, this person's riding up a hill. So the hill is kind of shaped like this, up and down. So my graph needs to be shaped like this as well. Well, that's not always the case. So you gotta just be careful. Just because the person's riding up a hill and your line goes up and down, the actual path that the bicycle follows goes up and down, doesn't mean that the graph's gonna look like that. So a couple things we can assume. If this person's riding up a really steep hill, they're going slow here, and then they're gonna be going fast up at the top, and then they'll be going very fast down at the bottom. So which one of these graphs represents something that starts off slow, then goes fast, and then is going even faster? Let's look at the first one here. This person's starting off going some speed, and then these speed values are decreasing. So if the speed was, let's pick a number like 30. If that was 30 up there, this is about halfway, so now they're going 15. And then right here, they're maybe going like 10, and then now they're going 15 again, and then they speed up to 30 again. So is that person slowing down and then kind of picking up a bit of speed and then all the way up? Yeah, that one looks like it could possibly be the one we're looking at. What about this one here? Let's compare it. They're starting off here. This is slow, and then they're going fast. So our speed is increasing. Is that one going to work? I don't think that one's going to work. If you started off slow and went fast, that doesn't really sound like riding up a hill. So even though the shape of this curve starts off here, goes up and down, and looks kind of like a hill, that's not going to be the one we want. How about this last one? Again, we're starting off slow, and then we're increasing speed, and then we have this one point in time here where we've changed from increasing speed, and then we're going at a constant speed, and then we're slowing down again. And this looks like kind of like the opposite of what we're hoping for as well, where we started off slow, then we're going fast, and then we're going slow again. So the best example here is this first graph. Because the person starts off at a speed, then they get to the hill and they start going slow, slow. They get to the top of the hill, and they start to speed up, and then by the time at the bottom of the hill, they're going really fast again, even though it doesn't look like the actual path the person follows. So that's just one thing to be careful of when we're looking at graphs. All right, number 2, draw a graph that is a reasonable representation of each of the following situations. This little 3 shouldn't be here, but it is, so it's fine. The temperature of water in a pot on a stove. So when we plot graphs, this one asks us to label our axes. When we plot graphs, we need to label the vertical axis and the horizontal axis. We need to write down what these things represent. So generally speaking, our horizontal or our x-axis is almost always going to represent time. So we start here at 0 time, and then time ticks away. So we're at like a minute, 2 minutes. It doesn't really matter, but we're going to have time there. And then this is also asking for temperature. So we're going to write in temperature up this axis. So time and temperature. All right, what is my graph going to look like? What happens to the temperature in a pot of water? Does the temperature increase or does the temperature decrease if you put a pot on the stove? What do we think? Should I start my line down here at the bottom, or should I put it up here at the top? generally speaking, the temperature should increase. So when we start, imagine I'm at home, gonna cook some pasta, fill a pot up with water from the tap, and I put it on the stove. So my temperature starts at like, I don't know, cold, coming out of the tap. You don't have to write in cold. And then we have hot. Temperature is increasing going up here, even though we don't have any numbers to represent that. So I'm going to start my line down here. What is temperature going to do when it increases? Everyone seems to be in a consensus that it's going to increase. Is my temperature going to go up forever? Is my temperature going to, increase or stay the same over time? What sort of line should I draw here? Will a pot of water increase forever? Or is there a limit to how hot water can get on a stove? It'll stay the same eventually. Yeah, so it's going to increase and then it's going to stay the same. So one other thing that we kind of need to figure out is my water going to increase and then stay constant? Or is it going to be something that's like a little more gradual where it stays, it goes up and then stays constant? Is there going to be, a sharp point there in the temperature? Or is it going to kind of be a curved line where it goes up and it should be horizontal at the top? Until you turn it off, yeah. If we then turn it off, then it's going to drop back down. So Alex says curved. Why are you thinking curved, Alex? You're right. Everybody seems to think it's gradual. Why is that? Why isn't there that sharp point, that kind of like a vertex in there? Anybody think of why that is? I guess might be a bit beyond math class for the day, but you guys are all right. It would be gradual. You think of heating up particles, they're moving, and then you got to heat them all up. So it's not like all of the particles are moving and then all of a sudden they just reach this temperature and just stop. Yeah, so it's definitely slowly increases until it gets to 100 degrees Celsius, depending on where you are, and then it'll just plateau off. So I'm pretty happy with my line. If you guys are, we can leave it like that. All right, the next one says your height over the course of your lifetime. So again, we need to label our axis. And this one's saying your height and then your lifetime. So lifetime kind of sounds like time. So I'm going to put time down here on the bottom. And then what are we trying to measure? Well, the other thing is height. So I'm going to put height over here. And I've labeled my axes. So you probably are just moved on and you've done all these, but we need to think about what happens to a person's height. My son right now, he's 8 weeks old and he's not very tall, if you could imagine that. So what's going to happen to him? Well, he's probably going to get taller. Do people generally get taller and taller and taller for their whole life? Or do you kind of get to a point where that's as tall as you're going to be? And then do you get shorter? Or what happens to a person's height over time? So you grow lots as a young child and less as you get older. That for sure makes sense. Do old people get shorter? Does anybody have like a really old grandparent who isn't very tall? What do you think? Yeah. So generally speaking, as you get kind of older, your vertebrae and things in your back kind of degrade and get closer together. So you actually do get a little bit shorter when you get older. It's kind of weird, but you do get shorter really slowly, but maybe a little bit. Some people it's not noticeable, some people it is. So, all right, we need to kind of plot a line to represent that. So I'm going to gather from what you guys have mentioned here that when you're young, you grow really fast. Like, my son, he's like this tall right now. In, 2 years, he'll be, about a meter tall almost. So you're going to grow really fast when you're young. And then you reach like 20-ish, and then you don't grow. You stop growing until you're pretty old, And then maybe when you're, 70, 80, you kind of get a little bit shorter. So when I draw my line, I'm thinking, okay, we got some fast growth. So that means the height is increasing at a really high rate at the beginning. So I'm going to have a really steep line at the beginning because I'm getting taller really quickly. And then your growth usually slows down when you get into your late teens. And then most of your life, you're going to be a kind of a constant, consistent height. And then when you get older, you may get a little bit shorter. Maybe not. Just depends on the person. So you might go down a little bit. So I would probably draw a line something like that. Now, generally speaking, although we didn't put it on our graph, this point in the corner here, we usually call the origin, and it represents 0 time and 0 height. Will you ever have 0 height when you're born? Should I have started my line from this origin and done something like that, possibly? This is kind of one of these tricky things when it comes to graphs. If I started my line right here at the intersection of these my axes, that means when you're born, you're 0 height, which is kind of a weird idea. So even though you could draw the line looking almost exactly the same starting right there, it just doesn't make sense to start it from the origin. So I actually moved it up a little bit, and we'll talk more about that later. I know we're just getting into graphing. This is important to leave a little gap here because, when you're born, you don't have 0 height. Your health over your lifetime if you smoke. Okay, so again, this is over the lifetime, so I'm going to plot my horizontal axis as time. Generally speaking, it'll almost always be time. And then we're going to have health here now. So what do we think about our health? If we're smoking, there was some statistics lately. We actually were talking about this the other day on our little lunch break. We have communal lunches. And we're talking about processed meats are now considered carcinogens, so they increase your risk of cancer. And somebody's saying, oh yeah, they're in the same category as smoking now in terms of cancer causing. So processed meats and smoking are the same. And there was a study that was published that said your percentage increase of getting cancer if you smoke is 2,500%. And if you eat processed meats, it's 18%. So although they're in the same category, they don't have the same effect. So, same with eggs. It seems like everything causes cancer. I was reading another article yesterday that said toast, because of like the burning particles on the edge of toast. The darker your toast, the more probability it can cause cancer. Kind of crazy. So, smoking, we know is bad for you. Lots of chemicals in there. Burning things into your lungs, not good. You're eating toast right now, Alex. Well, as long as you didn't toast it really dark, you should be fine. All right, so our health. Do we start with really good health when we're young? Or do we start with really poor health? So this kind of down here is like low health or poor health. And then up here we have, really good health. Our level of health, if we needed to quantify it or turn it into a number, starts really low, and then we need to get higher. So what's going to happen? Where should I start this line? And what's going to happen to the line? Will smoking make your health better or worse? This one's going to look a little bit different. All the other graphs we've looked at so far, we've had something that started down in this section, but what we're saying here is if we are plotting our health, generally speaking, when you're young, you have fairly good health. And then over time, your health would decrease. Now, would smoking be something that would, is it bad for you right away? Does it affect you right away, or does it affect you differently over time? And I guess there's a lot of debate that could go along with that. But generally speaking, I'm going to say that you're maybe going to start with really good health, and then your health would just kind of drop off. Now, I don't know at what rate, if you're going to have little bumps along the way, but I'm going to go ahead and just say that you probably would have something like that, and then, you know, eventually you would succumb to your smoking and maybe end up down there at the bottom. So I would probably draw on a line something like that. It's just, you know, I mean, there's no scientific evidence or anything that goes behind my little red line here, but if you think about it, you start with good health and you get worse as time kind of goes on. So I would probably start it up high and then go down low. So we don't always have to start at the bottom of a graph. We can start up at the top and go down. It's just kind of the way that worked out. All right, so a couple terms, dependent and independent variable. These come up from time to time, and it's important to know what they mean. Students kind of get confused by them. Even in grade 11, when we do grade 11 physics, there's a lot of graphing in physics 11, and we talk about independent and dependent variables, and they're easily confused. You get them mixed up. Even I get them mixed up from time to time. So let's make sure we write down proper definitions, and we can always refer back to this. So the dependent variable is a variable whose value is determined by the independent variable. You're thinking to yourself, Mr. Borden, you just defined a word with another word I don't even know yet. Like, what are you thinking? It's just kind of the textbooks or dictionary definition of dependent variable. So I'm not going to make you any happier with my definition of independent variable, but this is what it is. I didn't make it up. A variable whose value is determined, or sorry, is not determined by the dependent variable. Oh my goodness. Hey, that's kind of frustrating. These terrible definitions. So generally speaking, let's come up with something that makes a little bit more sense. So it would be like 1 plus A and B. 1 plus A equals B, and B determines, so it's independent. It kind of is like that, actually. I never really thought about it in terms of an equation like that. Let's go with this. Generally speaking, when we do an experiment, when we talk about this in terms of math, or if we're looking at some sort of situation, the independent variable is something we have control over. So let's write that in here. Take this guy, and generally speaking, we have control over that. So if we were doing an experiment, we would control the independent variable. If you wanted to think of it as like temperature, something like that. I don't know. We'll look at some more examples here. So a variable whose value is determined by the independent variable. So the dependent variable is dependent on the independent variable. The independent variable is the thing we're altering, the thing we're changing, and then the independent variable, or sorry, the dependent variable changes as a result of it. So we'll look at some examples here. All right, so we have a little chart here, a graph. And the first thing we do when we see any graph is we say, okay, what are the axes? And one really important thing about graphs is titles. So when we look at the title of the graph, day trip from Winnipeg to Winkler, Manitoba. And then we look at our axes. I see that I'm dealing with distance here over time. So I'm starting off at 0 distance and 0 time. So this is my start here. And then I'm doing something, And then at E, this is my end. I think just a coincidence that E was there at the end, but that's kind of what's going on. So we need to kind of determine what's going on. We need to interpret this graph, try to figure out what's happening. So the distance between Winnipeg and Winkler is 130 kilometers. So that's important. I wrote it in there. Here we go. From O, that's here, to A. So this first little bit of graph going along here from O to A. What's going on there? So the graph goes up and to the right. So as time increases, the distance from Winnipeg, does it go up or down? Are we moving away from Winnipeg or are we moving towards Winnipeg? What can we kind of determine from this little tiny graph here? So we're going from Winnipeg to Winkler. So Winnipeg is our start. Then Winkler is our destination, I guess. All right, so the graph goes up. The distance from Winnipeg increases. If I'm starting at Winnipeg down here, now I'm 20, at this point I should say I'm 20 kilometers away from Winnipeg. Here I'm 40 kilometers away from Winnipeg, and then just here I'm just over 60 kilometers away from Winnipeg. So it looks like it's increasing. So what can we describe as happening here in terms of the journey? So looking at the box down here, what's going on there? What could we say is happening? So point A here, if I drop down to my time on the bottom, point A is at 1 hour. So I guess this from O to A is the first hour. What happened? Well, we started at, we left Winnipeg, I guess. And how far did we travel? Some good questions here. Abby, why does the graph go down in the end? So we're going to actually, once we get to that segment, we'll talk about maybe what's happening there. And I think Alex's comment up above yours is kind of, really accurate. It looks like there's a horizontal line. So we'll eventually talk about what that means and things like that. Alex is ruining the surprise for everyone. He's way ahead of us. But yeah, Alex is right. They're going to end up going back home. And we'll see how that kind of works on the graph. So first hour we left Winnipeg, traveled about, it looks like this is maybe, I don't know, we'll just say 65 kilometers. And that was towards Winkler. All right, so maybe we'll speed this up a little bit because I think some of you are kind of grasping what's happening here. From section A to B, so we're looking at this little section in here now. What's going on in there, A to B? The line is horizontal, so what does that mean? If you think about their distance, let's say at point A, I'm just making this up, but at point A, their distance is 65 kilometers away from Winnipeg. At point B, their distance is 65 kilometers away. But what's happening to the time? Point A looks like it's at about 1 hour. And point B looks like it's at about 1.5 hours. So what's happening in that little section there from A to B? Well, the line is completely horizontal. So maybe they took a break. Maybe they stopped for gas. Alex suggested they stop for lunch. 30 minutes is a pretty long gas break, but the distance is staying the same. So the distance isn't changing. So when you have a distance time graph, isn't it 15 minutes? That's 15 minutes, you're right. This is 30 minutes in here. So Ava's a little bit ahead of me. Correcting me. Thank you, Ava. So what can we write? The car stops for about 15 minutes. Maybe we got some fast food. Maybe they took a really long gas break, line up at the washroom. Who knows? Make up your own story. All right, so that's good. The next section is from B to C. Got this next little bit in here. Now, one important thing is this over on the side here, where it says the distance from Winnipeg to Winkler is 130 kilometers. So if I look at my graph, I started at 0 down at the bottom here, and then I ended up, my last marking is 140, but this point C doesn't quite make it to that 140. So I'm going to assume that because they're not quite up at this line up above here, that's 140, that they're halfway between 120 and 140. So they're actually 130 kilometers away from Winnipeg, which I assume would be at Winkler. So I'm going to say when they get to C, they're at Winkler. Their distance is steadily increasing again. We have a line that's going up. So again, we're increasing our distance. So I'm going to say that the car travels about, again, it's about 65 kilometers, it looks like. And gets to Winkler. All right. From C to D, what's going on from C to D? Let's kind of think about this again. When we looked at A and B, we knew that the car wasn't moving. So it's looking like the same deal here. But we're stopped for a really long time. If I take point C, I drop it down. This is at 2 hours. And point D, if I drop it down, is at 4 hours. So how long did they stop for from C to D? So C to D again, we're staying the same. And yeah, even though point D is at 4 hours, they started at point C, which was at 2 hours. So don't just assume that they're here for 4 hours, because they had this beginning little bit where they started driving and then they stopped. So we're only concerned about the time between these 2 points. So 2 hours between those 2 points. So stayed at Winkler. For 2 hours. And then Abby had this question, and it is kind of weird, right? They took a nap. I know when I drive somewhere, I get there and I just take a sleep. You're right. Visiting, sightseeing, whatever. Maybe they had something to do, shopping. Although they started in Winnipeg and drove to Winkler, so likely not shopping. I've never been to Winkler, but I don't assume it's a large place. Mr. Ross, have you been to Winkler before? Negative. All right. So this last section here, we're starting at point D and going to E. So remember, This is where we originally started. So at point E, how far are we away from Winnipeg? We're 0 kilometers away from Winnipeg when we get to point E. What does that mean? It's just a funny way of saying, oh, we're back at Winnipeg already. They didn't stop on the way home. There's no little horizontal bits along the way and then drops down. So they just drove straight, right from Winkler, all the way back home to Winnipeg. So instead of the graph increasing the distance, now the graph is decreasing the distance from where we are to Winnipeg. So the distance away from Winnipeg is decreasing, meaning we're driving back. So what's happening? Car returns to Winnipeg. And it looks like it travels about 130-ish kilometers, and it took them about 2 hours to do that. I don't want to make fun of Canada Post because any one of you could have family who works for Canada Post, but that's probably true. I don't know. Canada Post isn't the most efficient sometimes. They get the job done though, right? Okay, so that's kind of what's happening on that graph. We've, your mom used to, see, that's what I'm talking about. I don't want to offend anybody. That's not my job here. All right, so we've kind of pictured what's happening on the graph. We've kind of described the journey, and now we have a couple questions to answer. So usually when we get questions from this sort of stuff, you generally speaking won't have to answer all these kind of intermediate things like what's going on along the way. So we're not generally writing all this down, but questions like the ones we're about to answer are likely to come up. So what was the total driving time? And then what are the dependent and independent variables? All right, so total driving time means time that they're moving. So let's have a look here. Looks like they're moving here for about exactly an hour. So this little stretch in here is looking like an hour to me. And then we have another stretch in here. How long is that stretch? Well, I think Ava mentioned that we're talking about 15-minute break, and then we have another. So that's going to be about 45 minutes. And then we also have the return home when we were driving, and that started at 4 and ended at 6. So this is 2 hours. So they were gone for 6 hours, but the question's asking how long were they driving for? So there was kind of 3 sections where they were driving. They were driving, they took a 15-minute break, they drove again for another 45 minutes, and then on the way home it was just a 2-hour stint. So if I add all those together, I have 1 hour plus 15 minutes, 45 minutes, 15-minute break. And then I have another 2 hours. So in total, that would be 3:45, or 3 hours, 45 minutes. So that kind of hopefully makes sense. The trip took 6 hours, so if the question was, how long did their trip take? 6 hours. How long did they stop for? Well, there was that 2-hour break and then the 15-minute break, so 2:15. Why does the graph start at 0 and end at 6? It doesn't really matter what it starts at and ends at. We could start it at 27, 28, 29, 30, 31, 32, 33. If we wanted to renumber the graph like that, that would have been fine. It wouldn't have changed anything. If I asked you how long did you drive for, if you started at 2 o'clock in the afternoon, you still drove for 3 hours and 45 minutes. So the time along the bottom doesn't really have a huge impact. It's just kind of convenient to start at 0 and then move forward in time. So dependent, independent variable, I told you we'd come up with this eventually. So let's start with the independent. And then we have the dependent. All right. The independent variable in this is what? When we look back at my definitions, I guess the definitions don't really help us here. The independent variable is time. And in this case, it's in hours. And the dependent variable is distance. And in this case, our distance was in kilometers. So the dependent variable, that doesn't make sense. The independent variable is time. So if we look at the definitions, a variable whose value is determined by the independent variable, variables whose value is not determined by the dependent variable, independent is time. We can't really control time, I suppose. So maybe that isn't the best kind of example. Yeah, that's just the way it is. We'll go with that. We'll look at more examples and hopefully it'll become a little bit more apparent as we move on. Generally speaking, the independent variable is going to be on our horizontal axis. And then the dependent is going to be on our vertical. Generally speaking. So, yeah, that's always the case for those. The last one here asks us to plot a graph. So they give us a scenario. Sarah went on a bicycle ride. She accelerated until she reached 20. She cycled for 30 minutes at 20 kilometers an hour. She arrived at the bottom of a hill. Her speed decreased to 5 for 10 minutes, and then she cycled up the hill. She stopped at the top of the hill. Sketch a graph of the speed as a function of time. Label each section of the graph and explain what it represents. All right. One really super duper important thing for this section is that you have some sort of ruler. Rulers are really handy for drawing graphs, and some of you have really nice hard-sided calculators that have straight edges. So if you don't have a ruler around, you can always use the side of your calculator. I'm not saying go buy a ruler, I'm just saying have a straight edge around so you can draw a graph. What I'm going to do is I'm going to plot some axes, or axes. So I'm going to draw a line down this side of my graph. And then I'm going to draw a line across the bottom of my graph. All right. Your calculator's edge has a ruler. It's like they knew you'd need a ruler at some point, so they did exactly that. We need to plot her speed as a function of time. Now, I said that almost always time will be on the x-axis, and that's going to be completely true here as well. So we're going to put time down on the bottom. And in this case, what sort of, in the question, or I guess the little paragraph, what sort of times were we given? Should I put time in hours? Because units are very important. Should I put time in hours? Should I put time in minutes, time in seconds, time in days, time in years, months? So what sort of unit of time was I given in the question? This is what I'm going to use in my graph. So if I go back and reread the question, looks like all of my times are in minutes. 30 minutes, 10 minutes, 10 minutes. So instead of plotting a time in hours or days or years, which is things I could do, there's nothing wrong with those, I'm going to put my time in minutes. All right, so we're happy with that. And then it says I need to sketch a graph of speed. So I'm going to put speed on this side. And what units were all of my speeds given in? Speeds are given in everything in my questions looking like kilometers per hour, kilometers per hour. So I'm going to go ahead and write down kilometers per hour. All right, so those are my axes. I need to actually put numbers in here to kind of represent all of these things. So this is where graphing gets tricky, is trying to figure out what numbers I'm going to put in, what I should start at my origin here, what do I want to go to in terms of values. Because I can pick whatever values I want. There's nothing wrong with picking sort of any values. But if I pick really, really big values, then my graph, instead of using the whole chart, if I had like 1,000 here, my graph would all be in this little section here. So I don't want to use values that limit the amount of chart I want to use. I want to use values that kind of maximize the real estate on my chart. I want to use the whole thing. So if I look at my question, what's the smallest time I'm given? And then what's the longest time I'm given? How long did this whole adventure take? So 20 kilometers an hour, she cycled for 30 minutes. So I'm up to 30. She stopped for 10, so that's another 40. And then she stopped again, top of the hill so I'm up to 50 minutes, is that right? Did I miss any times in there? Bicycle ride, accelerated, 20. Cycled for 30. $50 total, yeah. So I'll probably end somewhere around 50 or 60. So I'll give myself a little bit of a buffer. Go to 60. So if I went up by increments of 1, let's go 10, 20, 30, 40, 50, 60. Have I used my whole graph there by going up by tens? That doesn't work. So what I need to do is maybe double it. So I'm going to put a line here, another one here, another one here. How about if I put in 10, 20, 30, 40, 50, 60. If I do it that way, I'm going to end up kind of maximizing my graph. Even though there's this little bit at the end here where I haven't used it, that's okay. It's not going to work out perfectly where you use it. And when you pick numbers for your graph, always pick numbers that end in either 2, 5, or 10. Don't pick numbers that are like 1.25, 2.5, 3.75. That can get really confusing. So if you can avoid it, avoid it. We need to do the same thing with our speed now. So you accelerated until she reached 20. I guess we're assuming she starts at rest. So she's going to 20. And then at 20 kilometers an hour again, 5 kilometers an hour, and then stopped. So the maximum speed we're reaching is 20. So that means I want my speed to have, 20 somewhere in this area, trying to maximize the space there. So what can I go up with? If I started at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to run out of space. So I can't go up by 1s. That's not going to work. So maybe let's go up by 2s and see how that works. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's looking a bit better, so I'm going to do that. So 2, 4, 6, 8, there's 10, and then 12, 14, 16, 18, up to 20. you go up by 5s. If you went up by 5s, you would not quite use as much as possible.